Thank you, Karen. This is a little bit odd. I've never given a talk wearing a sweatshirt and my slippers, but it's very comfortable that way. The other thing that struck me is when I give a talk, I usually tend to focus on one of two types of people in the audience. I either notice somebody smiling and nodding approval of things I'm saying, and of course look at them often because that's very encouraging, or sometimes I notice somebody falling asleep and then I focus my attention on them and try and keep them awake. But this time I'll just have to stare out my window while I'm talking and try and imagine your reactions. The first slide, which is probably up right now, I can't see it by the way, is the title for the first third of the talk on this hypothesis that anthropogenic changes were large prior to the Industrial Revolution. And I call this kind of evidence top-down evidence because it's comparing this interglaciation, the last 10 or 11,000 years, with previous ones. And so the cartoon shows orbital elements, the tilt of Earth's axis and the eccentricity of its orbit, which change over cycles of 20,000, 40,000, and 100,000 years. And this means that we get a new interglaciation about every 100,000 years. And so we can compare the current one to the previous ones. Now, the comparison I'm going to show you here is comparison of greenhouse gases during those different interglaciations. And we can do this because geochemists working on ice cores have isolated bubbles of ancient air and analyzed carbon dioxide and methane in those bubbles and applied a time scale to the results. So the next slide should show variations. It's kind of a spaghetti diagram plot. It should show variations of measured greenhouse gases, methane at the top, carbon dioxide at the bottom. And the time scale for the current interglaciation is shown in red at the top of both slides. And the red circles are the measurements of methane and the measurements of CO2 for this interglaciation. The measurements of methane and CO2 for the previous interglaciations, which are referred to by stage numbers shown on the slide, are shown in different colors in both of these slides. And so these are the times in the previous interglaciations which are equivalent in age to or in timing to the last, in this case, 15,000 years of the deglaciation leading into the current interglaciation, which has lasted since about 11,000 years ago. If you look at methane at the top, you can see that I'm going to call the present interglaciation the Holocene at times. The present interglaciation comes up from low glacial values, the concentrations of methane, and they peak between about 13,000 to 10,000 years ago with an interruption, which I won't talk about, and then they decrease until about 5,000 years ago before increasing straight on to the present. Now, the previous interglaciations, it's a little hard to tell because they're all somewhat different, but they show the same basic pattern, lower values rising to a peak somewhere in the range of maybe 12,000 to 10,000 equivalent years ago, and then decreasing. But you'll notice that upward turn of methane in the current interglaciation after 5,000 years ago. You don't see that in the previous interglaciations. There's one interglaciation that has a brief 2-point oscillation there around 2,000 years ago, but then the methane concentration comes down and continues its downward path. So this is what got me started on this whole hypothesis. The Holocene or current interglacial trend, the rise for the last 5,000 years does not look like previous interglaciations. I call it the wrong way methane trend. The same is true, not quite as obvious, but true for carbon dioxide. At the bottom, you see the same basic trend for the current interglacial. The values come up to a peak around 10,000, 11,000 years ago. They start to decrease, but then about 6,500 years ago, they begin to increase. And the other interglaciations also show an increase to a peak somewhere in the broad range, 12,000 to 9,000 years ago, and then a decrease. Some of the decreases are very small, some of them are larger. One interglaciation, which I won't discuss here, but you may want to ask me about later, stage 15, the kind of pink-colored ovals, does show an increase throughout. So the carbon dioxide trend generally looks anomalous. Now, all these complications can be simplified with the next slide, which repeats the methane trend for this interglaciation in red, but it combines all the previous interglacial gas trends into an average shown in the dark blue circles and a standard deviation around that average. And you see for methane that the average of the previous interglaciations peaks at 10,000 years ago, about the same time as it does for the current interglaciation. And then both trends decrease through about 5,000 years ago, but the current interglacial methane goes up, and the previous interglacial average continues down. So that long-way trend of the current interglaciation stands out quite strongly on that plot. And the same is true, and even more so, for carbon dioxide. The carbon dioxide trend for this interglaciation sits right almost on top of the average of the previous interglaciation. And then after 6,500 years ago, it departs and heads up, whereas it continues down for previous interglacials. So the methane trend takes a wrong-way turn after 5,000 years ago, and the CO2 trend takes a wrong-way trend after 6,500 years ago. So if you want to be truly objective, you can call these wrong-way trends anomalies, but I made the case immediately that I thought they were anthropogenic, because if the natural trend is down and the current trend is up, then the only thing that's new about the climate system in the last 10,000 years is the presence of humans. So those divergences could mark the beginning of human influences on climate, and the second two-thirds of this talk will document that. There is two of these previous interglacial stages, 11 and 19, have been proposed as analogs to the Holocene because of the variations in the Earth's orbit. If you look at that part B session, I assume we advanced to the next slide. The precession trend for stage 11 is shown with a black plot, and it has about the same amplitude and a similar timing to the same trend in stage 1 shown in red. But there's another interglacial, stage 19, in green, which shows also a very similar trend. So based on the similar precession trends, the stage 11 was initially put forward as a good analog for this interglaciation. But it turns out, if you look at the tilt or the obliquity of Earth's axis, the stage 11 trend in black at the top is offset to the left from the other two trends. Stage 19 and stage 1, or the stage 19 and the current interglacial stage 1, are much more similar somewhat lower amplitude on stage 19. So stage 19 is the best analog. There are no perfect analogs, but it's the best analog. So part C in this slide shows the stage 19 CO2 trend, which peaks at an equivalent time of about 10,000 years ago, which happens to be about 787,000 years ago. And then it goes steadily downward like that average that I calculated for the CO2 trends. The Holocene trend peaks at a similar value, slightly higher, but the record sampling is much denser. And then it decreases in a somewhat similar way. But then again, around 6,000 to 7,000 years ago, the Holocene or stage 1 trend starts to increase where instead of going down. Now, when I published in 2003 this hypothesis, I projected that CO2 trends would have gone down to about 240 to 245 parts per million had it not been for humans, and so that red dashed line shows that projection, and that projection falls right on top of what actually happened in stage 19. This is data that the paper we're still working on. So my claim would be is that stage 19 is the best analog in terms of the changes in Earth's orbit for what should have happened to Earth's climate during this interglaciation. And humans were certainly not a major factor in global greenhouse gas concentrations back then. And so stage 19 is an experiment nature has already run, and it says greenhouse gas, it says that CO2 should have been decreasing for the last 10,000 years. Well, it did decrease for about 4,000 years, and then it rose. So that's more support for the early anthropogenic hypothesis. The next slide, which is a map, shows an experiment run for that interglacial stage 19 at the time equivalent to the present day, which was 777,000 years ago. So it uses the orbital configuration for that time and the greenhouse gas concentrations for that time. And the scale at the bottom in various colors shows how many months snow cover would have laid on the ground in the northern hemisphere under that similar orbital variation and lower CO2. And all the white areas are areas that would be permanently snow covered. Well, of course, it includes Greenland, which is a high standing and cold feature, but it also includes a huge area of Siberia and also Alaska, the Brooks Range, the northern Rockies, and a broad area in the Canadian archipelago, including Baffin Island, which is a feature about the size of California and Oregon. So what this experiment does, based on known orbital values and carbon dioxide measured from ice cores, what this experiment suggests is that everything shown in white would have 12 months snow cover, and if snow cover doesn't melt in September, late August or early September, it's going to be added to the next year. So that this is a map of areas that could potentially have been glaciated at the time most similar to today. The next slide shows, at the bottom it repeats that map I just showed you of the most similar time in interglacial stage 19. At the top it shows you an estimate we did previously. This is work with John Kutzbach and Steve Valvers and Feng He at the University of Wisconsin. It shows the same thing, months of snow cover for the projected values of CO2 and methane that I used in the original early anthropogenic hypothesis. And so you get almost identical snow cover, a little more in Alaska and northern Canada, but otherwise nearly identical. So that's just another way of saying that the stage 19 time, most like today, looks like the projection of where we would be right now had not been for early farmers. I'm going to skip this because it's not that important. So here's the cartoon that summarizes that finding, and it shows you global temperature on the left and the 20,000 years of record in the current interglaciation at the bottom. And you start off with very cold glacial temperatures, perhaps 4 to 5 degrees centigrade colder than modern temperatures. And then you have the rise out of the glaciation, a peak in warmth around in global temperature around 8,000 years ago. And then the top trend, the observed trend, is a schematic version of what temperature's been doing for the last 8,000 years, oscillating, but growing very slightly colder before launching off into the present day industrial era anthropogenic warming. Down below that trend is plotted what I call the natural trend, which is the trend that would have occurred had it not been for the greenhouse gases that farmers put in the atmosphere. And those are shown, the early anthropogenic agricultural greenhouse effect is shown in orange. So my claim 10 years ago was that we would have gone through the threshold of but needed to start the next glaciation sometime in the last several thousand years. But we didn't, because greenhouse gases from agriculture kept us out of it. We can skip now to slide 10, which shows a global map. So this is the second part of the hypothesis, and I call this bottom-up evidence of early anthropogenic changes, and this gets into the area that all of you work in, which is heavily reliant on archaeology. So this is global scale, big picture archaeology, and what's shown here is a map of the spread of agriculture, starting from the most prominent of the source regions of agriculture, and beginning to spread, shown in dark green, and beginning to spread out of those areas at the times shown in white numbers, which indicate thousands of years. So if you look to the Fertile Crescent in Southwest Asia, it's 9,000 years ago. If you look over to the Americas, it's more like 4,000 years ago out of Mexico. And China was another major source of domestication of crops and livestock. So this is the pattern of the spread of agriculture. And you note that the spread of agriculture is happening pretty much within that interval in which the greenhouse gases are going the wrong way. That is, that they're increasing when they should have decreased. Now, there's lots of data, much of which has just been very recently assembled, that bear on the timing of the spread. The next, I'm going to repeat here the methane pattern to remind you that somewhere between 5,000 and 4,000 years ago, the methane trend bottomed out at a value around 550 parts per billion, and then has been increasing ever since. And the slide after that shows a map of southern and southeastern Asia, put together by Dorian Fuller, who works at University College London. And he has compiled all the available data from archaeology, archaeobotany. Those are his areas of specialty. And what he's mapped here is the initial arrival of irrigated rice agriculture across that entire region. Now, Dorian he's both an archaeologist, but most especially an archaeobotanist, so he can tell whether he's looking at remains of dry rice or wet rice, and he can tell if it's been domesticated or if it's still wild. So this is a very nicely constrained map. And what it shows you is irrigated rice agriculture develops in the Yangtze River Valley of China around 5,000 years ago. And it's very small initial spread, 5,000 to 4,000, the two darkest colors on the map. And then by 1,000 years ago, it spread all the way down into Southeast Asia, Java, Sumatra, and across into India. And basically, by 1,000 years ago, being irrigated rice is being grown everywhere where it's grown today. At least the initial entry of irrigated rice has reached every area where rice is grown today. Now, Dorian took those data and he assumed that as rice first arrived in a given area, it would spread, it would become more densely farmed within that area based on population, on estimated population. And so he compiled a plot of the total area under irrigated rice agriculture from 6,000 to 1,000 years ago, which is shown in green. And he converted that area of rice agriculture to estimated methane emissions and to estimated methane concentration in the atmosphere, which are supported by estimated emissions with basically no significant lag. And he used modern relationships to do that. And what he got was an estimate that between 5,000 and 1,000 years ago, the methane concentration in the atmosphere would have increased by 70 parts per billion because of the spread of irrigated rice. The observations in the ice cores shown at the bottom of this slide suggest that the actual increase over that interval was about 100 parts per billion. So irrigated rice could explain about 70% of the wrong way rise in methane. But if you think back to two slides I've already showed you, the whole anomaly in methane has two parts. One part is the rise in methane, which has only happened at this glaciation, in interglaciation. But the other part of it is that in previous interglaciations, it fell. So the real methane anomaly is the sum of those two, and it's going to be larger than that 100 parts per billion observed methane increase shown at the bottom of the slide. So irrigated rice, in that case, is not going to explain 70% of the total anomaly, but something less. However, in this paper, which appeared in the journal The Holocene in 2011, Thor also mapped the first appearance of livestock, which are notorious methane emitters, again, using archaeological data. And you see that between 7,000 and 5,000 years ago, livestock occur in the Sahara, what's now the Sahara Desert. Back then it was a grassland because the monsoon ran stronger. Livestock on the Iranian plateau, which is an arid region, and in western China, which is also arid. So there were domesticated livestock in fairly broad areas, but none of them had high carrying capacity, so they're not likely to have had huge effects on climate, on methane emissions. But after 5,000, in that interval 5,000 to 3,000 years ago, methane livestock start to spread down into East Africa, all across India, and across most of China and Southeast Asia. There's some big holes in this map and a lot of work to be done, but basically, again, that same number, 5,000 years ago, methane emissions from this source, you can only imagine would have gone up, and by 3,000 to 1,000 years ago, you have domesticated livestock in all these regions. So livestock are going to contribute a significant amount to this story once they're fully mapped. So that's the methane story, and I would say there's pretty good evidence from archaeology that methane emissions are from agriculture are very promising for explaining the wrong way methane trends. The next slide shows that repeats that CO2 trend. Again, this interglacial in red and the previous interglacials in blue. And there are lots of data on this as well, although much of it is yet to be compiled, synthesized. One paper published in the 1990s by Zohari and Hopf shows the spread of agricultural remains out of Southwest Asia across Europe. And if you look at the scale at the top right, you can see that prior to about 9,000 years ago, most of the evidence is in Southwest Asia, coming into Turkey and a little bit of Greece. But the big jump across Europe in the evidence, this is all reliably carbon-14 dated archaeological sites. The big jump is after 8,400 years ago to 7,000, and then another jump 7,000 to 5,500. So by 5,500 years ago, agriculture is present in every part of Europe where it's used today. Obviously not as densely as it's used today, but it's there and it's beginning to fill in. And what's remarkable about this to me is that 5,500 years ago, we're still in the late Neolithic, the late Stone Age. The Bronze Age is still 1,000 years or more in the future. So people with axes made of flint are chopping down trees, burning or girdling them to kill them, and then burning the debris, and then planting crops in between the stumps. So even before the Metal Ages, we were doing major clearance, and this pattern, this timing of the big jumps at the green, light green, and the yellow colors is about the same, or brackets the 6,500 years ago reversal of the carbon dioxide trend. There's a recent synthesis of data from England, which is as far from Southwest Asia as you could get in the agricultural part of Europe. And you see the time scale on the left. So pollen, a synthesis of pollen remains, shows that somewhere around maybe 6,000, 5,000 years ago, you start to get hints that the woodland coverage, woodland pollen are decreasing. That becomes very evident by 4,000. And the The two lighter plots, light green and yellow plots, show semi-open pasture and meadow increasing after maybe 5,500 and certainly by 4,000. Also, this study, this is Woodbridge et al., compiled the density or the number of sites with C14 dates, reliable archaeological work, and you see a big jump around 6,000, and again, that's right after the reversal of the carbon dioxide trend. So all of this says we're in the ballpark to explain why carbon dioxide might have started climbing instead of dropping after 6,500 years ago because of agriculture. The same is true in China. There's a study by Li et al. A few years ago who again compiled the archaeological sites. And in this case, I don't know the detailed reliability about these sites. I suspect some of them are very reliably carbon-14 dated, and many of them may simply be correlated into the reliable dating by using the Chinese cultures, which succeed each other every several hundred years, usually less than 1,000 years. So if you have these cultures very nicely dated at several sites, then you can use places where you only have the cultural data and link into the carbon-14 timescale. That's just a guess on my part. It's hard to imagine all of this has reliable C14 dating. But anyway, the top map, for looking at China, 8,000 to 7,000 years ago, there's a sprinkling of sites in the Yellow River area and just a few in the upper Yangtze River. By 5,000 to 4,000 years ago, the Yellow River is crowded with sites, and the Yangtze River is beginning to become dense with sites. And remember that it's just in that lower map interval that irrigated rice begins to spread out of the Yangtze River area south and south. So that the lower part of that map in the next 1,000 and 2,000 years is going to get very dense with sites. So this slide shows that in that 3,000-year interval between those two maps, there was something like a 30-fold increase in archaeological site density, which means population must have doubled every 600 years if archaeological sites are linked to population, which you would think they would be in some way or another. So once again, evidence for major human presence on the land. All these people were farmers. So major increase in agricultural activity sometime between pretty much 7,000 to 5,000 years ago, which again brackets the reversal of the CO2 trend at 6,500 years ago. There's a very recent study in, I've forgotten what the source is, but by Dobson, John Dobson, that shows in the Yellow River where it goes upwards and off the map in that perhaps densest blob of green. It shows that people were burning coal for fuel and home heating because they had deforested that entire part of China, and that dates to 4,500 years ago. Coal outcrops in surface mines, so it was readily accessible, and that's all they had for heating, so that's what they used. So all this data so far says things were happening, major things were happening at the time that the carbon dioxide reversal occurred. Now, there's one problem, one criticism of the hypothesis that I think has been made, which has affected more people than any other criticism, and that is that there couldn't have been enough people to, even with this archaeological evidence I'm showing you, there couldn't have been enough people to drive the carbon dioxide increase. And this is particularly true between 6,500 years ago and about 3,000 to 2,500 years ago. You see I think I meant to say advance to the next plot. This would be number 19, slide number 19. The carbon dioxide trend comes up pretty rapidly, 6,500 years ago to 2,500 years ago, whereas the conventional estimates of population rise much later, mostly after about 1,000 years ago. So you have this problem. If humans are causing the CO2 increase, how come the CO2 increase occurs way before the population increase? That doesn't seem to make any sense. I think there are two answers to that question, one of which has emerged and one of which is emerging. There are historical data from China and from Europe, very, very spotty, but enough to catch the trend, I think, of land use going back 2,000 years. And the top slide, if we're now on slide 20, shows hectares per person in China. Now, this is hectares per person. This is cultivated land, actual crops, not pasture, not hay fields, not other areas cleared just for the wood. So this is crops per person. So you see a downward trend from the year 5, I think, is the first data point during the Han Dynasty, down to much lower values in the very late industrial era, with values of 0.25, 0.2 or less coming into the industrial era. So what that means is that people were using about 4 times as much land per person for their crops 2,000 years ago as they were using in the very late pre-industrial times. And the bottom plot shows a similar but different index, which is hectares cleared per person, in other words, deforestation in Europe. And in this case, this index does include pastures and meadows and land burned for other purposes. And so there are many more hectares per person than the plot at the top. But the trend is quite similar. You go from 6 or 7 hectares per person deforested in Europe 2,500 years ago to about 1 or 2 in the last few hundred years. Again, about a factor of 4 decrease. So what this means is that even though populations may have been lower or were lower back in time prior to the last couple of thousand years, these people were clearing at least 4 times as much, using at least 4 times as much land. And as you get farther back than 2,000 years ago, we don't have data, but you can only imagine that it remained at least as high, or was perhaps there was even more clearance. Someone who has played if we go to the next slide, which shows a cartoon of some trees, the person that first really shined a spotlight on this issue was Esther Ballstrom, who was an economist who published 2 books in the 1900s, 1965 and 1981. And she looked at modern populations of hunter-gatherers and people in various stages of cultural development. And she concluded that early agriculture was very inefficient. And so people used much more land per person because of the lack of efficiency which developed later. Back 5,000-6,000 years ago, fertile, well-watered valley soils were available for farming, so whoever came in took as much as they needed and used that land inefficiently because they didn't need to be efficient. And the way they used it's probably suggested by this cartoon that you start with mature forest. You clear off the trees and burn the residue, and you can farm for 2 or 3 years, especially because the soil is enriched by ash from the trees. It's sweetened, and so you can farm for 2 or 3 years, but the soil plays out, and then you have to move on. And so you move on and you clear another. This would be maybe an hectare or 2 to farm that. Meanwhile, out behind you, the shrubs and saplings start to come in, and then larger and denser saplings, and then later on small trees. Well, the big gray arrows show that these people, as they moved around, were leaving a trailing footprint of trees that had not yet grown back. So those gray arrows represent carbon that is in the atmosphere and has not yet gone back into the cleared land. So that's one of the things that makes the footprint much larger. Later on, people discovered things like manure, and much later crop rotation, and that. So you go from people moving around constantly every 2 or 3 years to, in the last few centuries, people farm the same land every year and maybe get 2 crops a year out of it. So that's called intensification, and what it represents is much less land use per person. The effect on this on the amount of clearance is only becoming evident in the last couple of years. The next slide shows a map, a couple of maps. At the bottom, labeled C, is a map based on the assumption of people have always cleared the same small amount of land as they did in the year 1800 or 1850 or 1900. And if that's true, there really hasn't been much forest clearance at all. So you get a map that shows 80 to 90% natural vegetation across almost all the continents. You see a slightly lighter green color in Europe and in Southwest Asia and in northern China, but very little clearance. But if you use that historical data of higher clearance in the past, decreasing towards the present, you get a very different picture. That's the map at the top, which shows lots of clearance in Europe, Southwest Asia, India, China, and lots of clearance in, this is a map for 2,000 years ago, I forgot to say, lots of clearance in Mexico and in the Inca-dominated empire in South America. The map at the top, again, this is a model based on an assumed amount of clearance per person, looks much more like a map published in the Cambridge Encyclopedia of Archaeology in the 1990s with all the dark green areas having what is called complex stratified agriculture. Those dark green areas are a pretty good match to the areas that the top simulation shows as deforested. As you come forward to 1800, I forgot to mention this is work by Jed Kaplan and his associates in Switzerland. As you come forward to 1800, you bump up against an interesting constraint. If you make that assumption that farmers always cleared the same amount of land per person and it was small, you end up with an estimate that Europe was, as of 1800, no more than half deforested, except a few areas, including Spain. That most of it was 50 to 70% forested at 1800. And the reason this is strange or odd or impossible is that there's good data showing that countries in Europe began to reforest after 1800 because of the increasing efficiencies of intensive agriculture. So countries in Western and Central Europe reforested in the last 200 years. Well, if they hadn't deforested by 1800 and they have subsequently reforested, then you ought to see predominant forest all over Europe. Well, of course you don't. Most countries, until you get up into parts of Russia or maybe around the Baltic, most countries are 80-85% deforested. So the map at the left shows what you get if you assume that early clearance was intense, as shown in those plots I showed you earlier. You get much more clearance by the time you get to 1800. In fact, you're down in the 90% to maybe 60-70% deforested, and those numbers are reasonably consistent with the fact that Europe has, if anything, reforested in the last 200 years. So these maps pretty much require that early clearance was much more intense than the first of these early land simulations suggested. One last subject or issue is here. The next slide repeats that carbon dioxide trend, rising early, and the population trend rising late. The population trend there is a schematic. There's actually fairly decent population data back to 2,000 years ago, so there are many more zigs and zags in that population curve. All population curves prior to about 2,000 years ago are projections, and the classical technique is to use a geometric population increase, which I can describe in two ways. One way, quite simply, is it means the population doubles about every 1,000 years, and so most of the rise occurs late in the curve. And another way of saying it is that the fractional rate of population growth is constant all the way through those 7,000 years that are shown here. So whatever the population is at a given moment, a fractional population growth in the next year or century or what have you is the same. And if you think about it, that's a rather strange assumption. I mean, 7,000 years is a lot of time, or the 7,000 years that are pre-industrial. That's a lot of time, and it's hard to believe that that population, that the environment would be consistently conducive to exactly the same rate of population growth. So there's another view, and this is finding some support in DNA evidence. The next slide repeats the geometric cartoon, somewhat different time scale, but it also shows a logistic, a trend that's labeled logistic, and you notice that population slide, that population comes up much earlier and then levels off. Well, the logistic population curve is one that's widely used by ecologists and paleoecologists, and what they assume is that growth rates are fastest early on when resources are abundant. In the case of farmers, it would be fertile soils, well-watered soils in valleys, but they slow as population increases. The growth rates slow because people are now forced to farm up the hillsides, less well-watered, less fertile soils, and also disease starts to play a role and whittle away at the population. So these logistic curves are going to push the rate of early, if they turn out to be correct, and I mentioned that there's DNA evidence that supports it, that that's the case, they're going to push the population growth farther back in time, which is going to push the CO2 curve that they can, the carbon emissions curve that they can support back in time. So this is perhaps the major issue I'm dealing with right now, and trying to work with some colleagues who have the expertise to do that, to see what is the most reliable population curve, and will it explain the early CO2 rise. The higher per capita land use reconciles part of that mismatch, but the earlier population rise should also help. One last slide. This is in a related subject. This is slide now 26. The carbon dioxide curve from a high-resolution ice core, so now you're looking at the last 1,800 years, and also methane at the bottom for the last from 1,000 to 1,800, shows very coherent oscillations in both greenhouse gases, and they both have dips. Now remember, in both cases, the curves have been rising for thousands of years to get into this area of high CO2 and high methane. But then they start to show some dips, and 200 to 600 AD for the CO2 curve, again 1200 to 1400 for the CO2 curve, a really sharp drop between about 1525 and 1610 for CO2, and then the methane dips shown at the bottom. So in the middle, I plotted the major depopulation events, that is, major crashes of global population over that same interval of time, and you'll see that both Europe and China had population decreases that were quite sizable, 5 and 7.5% of global population during that same interval, 200 to 600, when the CO2 values were going down. Another decrease in China, and after 1200, that's Genghis Khan and his successors. The Black Death in Europe, there 1350, and then the biggest disaster of all, the 50 million people who died in the Americas because of contact with European diseases to which they did not have immunity, along with some loss of life in China. So there's a pretty remarkable correlation between losses of people and dips in the greenhouse gases. My claim here was and is that let's take the Americas. If almost all Native Americans, not all, have used agriculture along with hunting and gathering, and if they're clearing large areas of, say, the Mississippi and Tennessee River valleys, but larger areas also in Central and South America, if 80 or 85% of them die due to diseases between 1525 and 1600, then forests start to grow up where they used to farm and sort of take CO2 out of the atmosphere. The methane decreases probably involve in part, things like Genghis Khan ripping up the irrigation infrastructure in China and having livestock starve as a result of people dying and the livestock not being fed. So there's a lot of plausible links between lots of millions of people dying and greenhouse gas decreases. So as I said, that's almost another story, but it's a very interesting one and at a more recent time scale. So you get the sense from my tone that I think the data are coming in to test the hypothesis, and that book review in Science that Karen read earlier, that's the process of science working itself out. And my sense, of course I'm biased, but my sense is the data that are coming in are coming in behind the early anthropogenic effect on climate and not behind the criticisms of the hypothesis. So with that, I throw myself open to any questions.
Bill, thank you for a fascinating talk. Are there questions? You folks are not on mute, you know. You can speak up.
Bill, I'm wondering if the loss of buffalo herds would have had any effect on methane in particular. You know.
I guess that's something I don't think about much, but what I remember would be there were, of course, 12,500 years ago, there was a mass extinction of large mammals in the Americas, and a lot of those were methane emitters, and then they were gone. And then, as I understand it, what probably happened was that the survivors, like the buffalo, then proliferated, and so you basically replace one kind of methane-emitting wild animals with a more selective group of methane emitters. What that would do to global climate, I don't know. But I think if you look at the numbers of livestock around today, and I should have a number at hand, but I don't. It's a huge number. I don't know exactly how it would compare with the buffalo, but
so the bison, the American bison, I guess, is what they really are. Would be replaced by domestic cattle.
Yeah, for a while. When the livestock, for instance, go down into Africa, it's probably just a replacement scenario where the livestock edge out the wild animals, and there's no net increase in methane. But after a while, if people have huge livestock herds, then you start getting the excess of methane. But an area like China, which used to be forest and now becomes suitable for livestock, that's really pretty much almost all the livestock are a net increase over previous levels because there weren't that many grazers, browsers in the forests.
Good point. This has just been fascinating. Thank you so much.
Thank you.
Yeah, Bill?
Yes.
Hey, this is Brennan Carter calling from Sitka, Alaska. I read some of those papers you wrote back in the early 2000s as part of my dissertation research, and it's good to see that you're following up on that because it seemed very compelling. Some of that early work was very compelling. What I was wondering is whether the thing that popped in my mind and has sort of kept with me for the last 10 years is the problem of stochasticity, in that when you destabilize a system the way that it seems like it's been destabilized, or it's been artificially stabilized, I guess, at a high level, and seems to be going in an opposite direction of where the Milankovitch curves would normally take us, whether that's a problem, like if the carbon sinks catch up and all of a sudden we get plunged into a new ice age.
I thought you were headed in one direction, then you went in another. But in effect, my original hypothesis and still my claim is that we would be in the very early stages of a new ice age if we had left nature alone. As in those maps of simulated months of snow cover show that the areas in the northern hemisphere with 12 months snow cover, which is to me the same as incipient glaciation, they were 30% larger than the present day Greenland ice sheet. So it's not a huge area, but it's not a small area either. But so that I say it would have happened sometime in the last 2,000 years that we would have those areas glaciating. But the farmers stopped that. Now, of course, I think we've stopped any natural glaciation, which should have happened 2,000 years ago. We've stopped that for tens or hundreds of thousands of years into the future. So we've
you think that, so we may skip the next cycle?
Well, I think we already have begun to.
Oh, wow. Okay.
The insulation curves, the summer insulation curves guide glaciation in the northern hemisphere, and they don't really get any lower than they have been for the last 1,000 years until about 60,000 years from now.
Oh my
goodness! But we have a 2.75 million year record of glacial cycles, and there's never been a 60,000 year long interglacial in all that time. So I think we've already done it. I mean, it's really quite remarkable that these glacial cycles, 2.75 million years, and we've already stopped them.
Yeah, that seems pretty dramatic.
Yeah, well, it's I'm not a dramatic person, but that's a very conservatively thought out conclusion. It doesn't sound like it, but it is.
So, I mean, addressing the stochasticity part of it, do you see any increase in the potential for having rapid, broad-scale climate switches, kind of like what we saw at the end of the Younger Dryas, or at the beginning and the end of the Younger Dryas?
Yeah, I skipped over that. The Younger Dryas looks to me like one of those. During times when large ice sheets are present, you get fairly large flips in northern hemisphere climate in particular. But the Younger Dryas is the last big one, and once you get into a full interglacial, you just don't see them anymore.
Okay.
So temperature hasn't changed much, maybe certainly less than a degree centigrade in the last 8,000 years. So I don't think, and I don't see them in the future. That there are some people like to talk about that possibility, and it's impossible to rule out. But I think the future looks, even if it's just slow and gradual warming without any dramatic warnings, it looks bad enough without adding a flip, some kind of flip.
Yeah, that was the thing that really sort of I won't say it freaked me out, but it's the data seemed like, I mean, essentially it's at this point it's almost like a majority human influenced environment, and we just don't know. I mean, how stochastic the system is going to be on a short-term basis, over a period, human experience, single generation human experience. Just, I don't know that we've been there in recorded history,
Well, yeah, it is hard to predict. I would say that on the last 200 years of climate change and on projections of climate change, I'm a mainstream climate scientist. I'm not in any way a skeptic. The only thing that I'm adding to the story is that when we started to warm things up after 1850, we were building on 6,000 or 7,000 years of prior effects on greenhouse gases and climate. So in my view, it started from a different, lower baseline, but I have nothing to say that would change the mainstream community view on the current global warming and and the future of global warming.
Yeah, have you seen Bill Webb's stuff on palynology and charcoal deposits in the eastern United States? His palynological work.
Who did you mention?
It's Webb, William Webb.
Oh yeah.
Yeah, because I recall that you see a big blip in carbon like at I want to say 8,000 or 8,500. It's almost like there's some intensive forest clearing going on in the eastern United States. It'd be really complementary to the early.
I was a member of the COMAP group that Tom Webb and John Kutzbach were heads of.
Okay.
And I don't remember anything like that. What I remember is pretty much a slow, steady march towards warmer interglacial climates, and I think they had a little bit of a reversal to cooler climates about 2,000 years ago because, if I remember right, spruce trees moved back south. They had been retreating north during the deglaciation, and then they stabilized, and then they came a little bit south. So it got a little cooler or a little wetter or something like that, but it was very small.
Yeah, I was thinking more of their charcoal data seemed to show early forest clearing. So
I don't remember them.
If I can interrupt you guys, there was an article in Science within the last 5 years that talked about an increase in carbon with the extinction of megafauna.
Right.
And that might, I don't know if that's the blip that you might be thinking of.
Yeah, it probably is.
Well, I thought he was talking about the last, 8,000 years ago, and that's back about 12.5 thousand.
Oh, okay.
I'd have to go back and look at the web papers.
Okay. Anyone else want to chime in?
Hi, this is Marcy with the National Park Service, Marcy Rockman. That was a really interesting presentation. I'm still trying to wrap my head around some of the comparisons. I think I'm still feeling my way through my question. I'm still, trying to wrap my head around the comparison between, say, the inefficiency of early agriculture and what that would have done in terms of carbon contributions to the atmosphere compared with, say, our modern capacity to contribute carbon to the atmosphere sort of per person or per acre. I'm trying to remember if you mentioned any publications or analyses of that. So I'll just ask now, do you know of any studies that have been done, or could you point me in the direction of anyone who might be looking at? Because I'd be really curious to look at what might we estimate some early agricultural carbon contributions compared to modern carbon contributions, say, per person or per acre?
Well, I showed the name Kaplan, Kaplan.
Uh-huh.
He published a paper. It was also in the Holocene. It's got a 2010 date on it because that's the date that I guess it was accepted online. But it's in the same Holocene volume as the fuller work on the rice agriculture.
Okay.
And he's the one that used the historical. Well, he actually went back and dug out some of the historical data that people had assembled in the late 90s, and the name just escapes me, but it's somebody from the UK had compiled a lot of data on early land use. So anyway, his name is Jed Kaplan, and if you get access to that Holocene volume, he's got maps starting at, 10 or 11,000 years ago and coming right through to the present of percent land clearance and carbon emissions region by region and sub-region by sub-region. It's a very comprehensive paper.
Gotcha. Thank you.
Sure.
Are there any more are there comments or questions for Bill? Bill, I have something. I'm going to reveal my ignorance here. When You talked about the methane contributions of domestic crops. Could you talk for a minute about what exactly the mechanism is? Is it the difference between C3 and C4 plants?
Oh, yeah, this is one of those talks I always skip over something, and I left that out. Methane, anthropogenic methane, it comes from irrigated rice because what rice paddies are is basically anthropogenic wetlands. Methane comes out of natural wetlands as swamp gas or bubbles up from stagnant water. Well, rice paddies are anthropogenic wetlands, and so they're quite rich in carbon. So they feed methane into the atmosphere. Methane comes from livestock. I like to say at both ends, from both ends.
Yes.
And
the
it comes
livestock part I understand.
And it also comes from burning crops and weeds. If you have a pile of debris and you set it on fire, and if the bottom layers are not getting any oxygen, then the carbon goes into methane instead of into carbon dioxide.
Okay. So that's why you're also, even though obviously people in Europe are not growing crops at any one time, you're tracking the methane release as a byproduct of farming.
You do get some from farming that way. I would guess that since livestock came into Europe along with the crops, and particularly cattle, that I would guess that the domesticated livestock were the major emitters of methane in Europe, and it's cattle and goats and sheep and pigs, all of them domesticated in Southwest Asia.
Uh-huh. Thank you for that.
You're welcome.
More comments? More questions? Well, Bill, thank you very much for a fascinating talk.